couple of things in this question. So I want to use this question to help you with the tension tutorial and also to help you with connected objects. So we've got essentially we've got a 1 kilogram rope, a 5 kilogram block, that's 6 kilograms, and a 9 kilogram other block. Sorry, 5 plus 1 plus 3 is 9. So we've got a 9 kilogram system. Maybe I'll start there. So I'm jumping ahead a little bit. If I see a connected object problem, I immediately sort of think about systems. And like, can I group things into certain systems or into certain groups? So here, I definitely, to figure out the acceleration, I know the thing that holds all the things together, like what's common is the acceleration of the system. Acceleration of the A, the same as that as the rope, the same as that B, because they're all moving together. So to get the acceleration of the system, so I guess if I need, I'll do it all over here. A system is equal to F net system. So again, this is going back to that first slide where you got to match all of these subscripts have to be the same. So it can't, A of the system is F net of the system is mass of the system. So the only thing that's pushing on the system to the right is the hand. If I group the whole system together, there's no friction forces. So I sort of did this in the tutorial. So remember messing up this envelope. And I made the numbers nice, so you don't need you don't really need your calculator. It's 4.5 newtons of a pushing force on a 9 kilogram system, so everything's nice and round here. So it's just half a meter per second squared. Okay. No problems there? So it's actually much easier to think about. You have a couple of ways to do this. So I am asking about the tension forces on the rope. So I could think about drawing the free body diagram for the rope. Let me get a couple of colors here. So I know that the rope has and again, this is where I kind of messed up here. I would say, what is the horizontal component of the tension force on the rope by block B? So this is on the rope by B. And I'll do a different color here. This is the tension force on the rope by A. Now I know that this, in a sense, I can start with maybe thinking about how big is the net force on B? Sorry, net force on the rope. The mass of the rope is 1. Acceleration of the rope is 0.5. So it's half a newton, right?
I have a quick question.
Yep.
The problem says that the rope itself has a mass, so are we taking into account is there a dip in those vectors?
There would be, but I should have stated it just looking for the horizontal components.
Okay.
Yeah. Otherwise, it's way too difficult. So this will be just 1 kg times 0.5 meters per second squared. So that's half a newton, but that's only the net force. Okay. So I know that T or B has to be half a newton bigger than T or A. That's what I know so far. Okay, any volunteers for what step I might make next? Too shy?
You know that, you can read, from Newton's third law, you know that the tension on the rope by B is the same as the tension on B by the rope. And you know that B only has 2 forces exerting on it, one of which we know. So you can just do F net equals 4.5 minus the tension force equals mass times acceleration.
Okay, just want to make sure everyone's recording here. So so you could look at B or you could look at A. B is a little more challenging, but we could think about the free body diagram for B. So I'll do that in this space here. So B has this probably a normal force on B by the hand, which we know is 4.5 newtons. Okay. We know there's a tension force back on B by the rope, which is what is a third law force pair with the tension force on the rope by B. What is the net force on B? 1.5. So that's where 1.5 newtons comes in. So the net force on B is 1.5 newtons to the right. mass times B times acceleration of B. So if I have a 4.5 Newton force to the right, but I only want the net force to be 1.5, how big is TBR? 3, right? And if TBR is 3 newtons, how big is TRB? 3 newtons. So the 3 was the correct answer for our first question. And since you know the net force on the rope is half a newton, how big is TRA? 2.5. Can I suggest another way to have solved for the 2.5?
You could take the, like, you know the only force acting on A is by the rope, and you know the mass and acceleration of A. So you can just find that force and then find the difference.
So this is almost a point I'd recommend. I would actually start with A. It's the simplest of the three. It's of the three objects. It's the only one that has one force to the right. So A only has a net force of the pulling force here on A by the rope, and that is the net force on A. Happens to be the horizontal component. So it's a 5 kilogram block moving with an acceleration of 0.5. So I mean, that's very quickly could get to that 2.5. So if that's 2.5, this is 2.5. So working in a different sort of order, if I start with A and think about 2.5 newtons, and then I know the net force in B is 0.5, then I know that the TRB has to be 3. That might have been my logical process. But it doesn't matter which way, all are valid, of course. Any questions on the quantities? No? All good? So, yep. Multiply the mass of B, of B. The mass of B times the acceleration of B. So it's a 3 kilogram block accelerating at 0.5 meters per second. So 3 times 0.5 is 1.5. Right. Yep.
Real quick, so the F net of B is 1.5. So to find the T of BR, you just have to think what minus what will give you 1.5.
Yeah, and technically, if you do it mathematically, so we know that F net B. So if this is like why it's a subtraction or in a sense adding, is the NBH minus the TBR. So you're writing a second law equation. So if I'm trying to solve for TBR is equal to NBH minus F net. So that's why it's equal to 4.5 newtons minus the 1.5 newtons, which is why it gives you 3 newtons. But sometimes you can get lost in the math and not think about why the steps are this way. I think it's either you think like, well, if I got 4.5 to the right and I need a net of only 1.5 to the right, well, the other one has to be 3. Okay. So the other thing the idea I want to point out here is that we can see that the tension in a rope that has mass is not equal. The tension on one end of the rope is not the same as the tension on the other end of the rope. And then we're going to do the next problem, but we'll do that, I think, let's see.